Thanks a lot, Floriana, for this introduction. First of all, I would like to thank the organizing committee for this invitation. I'm really honored to be here to deliver this talk. As Floriana has introduced this presentation, the idea is to bring here to discuss the experience, the efforts that we made at Politecnico di Milano in the development and validation of a data set of simulated motions from physics-based numerical simulation. So the idea is just to provide our insight in the construction of this model, of this data set. The data set is called BB-SPEEDset, and the main goal of BB-SPEEDset is to provide the earthquake engineering and the seismological community with motions, simulated motion, that can be used in addition to recordings. In those conditions where, as we know, the recordings are sparse and are not enough to characterize the earthquake ground motion. Very quickly, the numerical approach that was used to construct the dataset, BB-SPEEDset, is SPEED. The SPEED was introduced before by Roberto in his talk, so I don't want to enter into details. What I want to point out here is the richness of information that you can get from a physics-based numerical simulation. As you see from this slide, for a single simulation, you have information about the spatial variability of ground motion, as you see from this snapshot. At a single site, you have the three-component ground motion time series that are particularly important for all the earthquake engineering application in response history analysis. When constructing a data set of simulated motion for engineering application, it is very important to construct, to have broadband ground motion that are motions with sufficient energy content in a broad frequency range that is relevant, that matter for engineering application. So still, even though we are pushing the limit of numerical simulation forward and forward in frequency extent, our simulation are still band limited. So we need to inject simulated ground motion in the high frequency range to construct broadband ground motion. And the approach that we followed is the one that Roberto mentioned before, is the approach based on artificial neural network to construct broadband ground motion starting from the results of physics-based numerical simulation that are typically limited up to 5-10 Hertz maximum. This slide shows an overview of all case studies that were addressed by SPEED in the last, let's say, 10, 12 years. What I want here to point out is that the case studies cover very different regions, multiple seismotectonic contexts. So you pass from Turkey, 2023 earthquake, down to very low seismicity area like France, or induced seismicity area like Groningen. And the magnitude range that is sampled by our SPEED simulation is very various. So you have magnitude as low as 3.2, to magnitude as high as 7.4, like for the Istanbul simulation that Roberto showed before. For the construction on BB-SPEEDset, we collected a considerable number of this simulation, and we post-processed in a homogeneous way according to the workflow that I showed in the previous slide. So for each simulation, we ended up with a number of broadband ground motion. BB-SPEEDset is in continuous development and construction. So you see in the slide that we started from the version number 1 2 years ago, more or less, and now we released a new version that is version 2.3, and this version includes the simulation that are highlighted in blue in this slide. You see that it covers regions in Italy, in Europe, and in the world in general. This slide shows the main feature of BB-SPEEDset, the current version of BB-SPEEDset, and in particular, you see on the left-hand side, you see the magnitude distance distribution of BB-SPEEDset, and in particular, you see that it covers earthquakes with magnitude between 4.9 up to 7.4. So it covers a rather broad range of magnitude and different focal mechanism, with a predominance of normal mechanism because we focus mainly on historical earthquakes in Italy, where there is a predominance of normal focal mechanism. In this plot, on the left, you see in red the BB-SPEEDset in blue, and you see in red also the magnitude distance distribution of the NES dataset. The NES dataset is a dataset of near source records that was developed in a completely independent way, is near source recordings. This is important because it's the reference dataset that we consider for validating the simulated dataset. As you see on the right-hand side plot, the site conditions that are sampled by BB-SPEEDset are various. So you see that it includes the sites considered vary from very soft site with shear wave velocity VS30 of 200 meters per second, up to very hard rock site with VS30 of 2000 meters per second. The BB-SPEEDset is distributed as an open source file, as you see here, and it was constructed, also a flat file was constructed, and the flat file was constructed following the similar standards, the same standards that are used also for recorded data set. So the most relevant, the collection of the most relevant metadata and ground motion intensity measure. And notice that the BB-SPEEDset is distributed as also in terms of 3-component accelerograms, and in particular, the present version of BB-SPEEDset includes 20,000 ground motion waveforms. It is important, of course, when distributing data set of simulated motion, it is fundamental the validation of the data set. This slide shows the conceptual framework for validation that we attempt to use to validate BB-SPEEDset. I don't have the time to enter all the details of this validation framework. I just want to point out the main feature. The validation may involve different aspects, is a multi-level validation framework. In particular, there are 3 different levels, and it should cover different metrics. On the left, ground motion intensity measure, so a seismological perspective, and on the right, engineering demand parameters, response variable of engineered system, like the interstory drift ratio, the ductility, or the permanent displacement in case of geotechnical system. The 3 levels of validation involves the first level, the historical earthquakes, that is the real earthquakes for which you have recordings available site by site. The second level is a level that involves data set, entire data set of scenario earthquakes, as I will show later. And the third level is more focused on code-based engineering application, where you typically select a suite of ground motion according to prescribed code-based criteria, and you use them for the analysis of various engineering systems. Note that validation must be performed in a broad frequency range, because looking at the engineering application, we are interested in a broad frequency range. And also I would like to stress that here there is a level that is masked, that is hidden, that is the spatial scale. Also, the simulated motion should be validated also in terms of the spatial variability, so spatial coherency, and also spatial correlation of intensity measure. In the next slide, I will go through these 3 different levels with reference to the validation of BB-SPEEDset. Here, Roberto before has already showed a case of validation against historical earthquakes, because in Roberto's talk, the case of Istanbul was considered. Here, I just want to stress that in most cases, included in BB-SPEEDset, the simulation were validated against real observation, against recordings. As you see here in the slide in red, all the red cases are validated against historical earthquakes, where you can compare the output site by site. You can compare the output of the simulation with the available recordings. What about level 2 validation? This is particularly important, interesting in case of dataset of scenario earthquakes. And here I think that the validation should address 2 main questions. For a given magnitude and distance range when compared to recorded dataset, are the ground motion intensity measure collectively unbiased? And what about the ground motion variability? Do the ground motion reproduce a realistic variability? Again, the idea is to make these checks for a given magnitude and distance range, and the degree of realism of the data set should be evaluated in comparison with the available recordings. This slide shows some validation tests, a selection of validation tests on the distribution of intensity measure that were done on BB-SPEEDset in comparison with the NEST dataset. And in particular, you see in the slide on the left the correlation between long period, short period spectral acceleration. On the center, you see different cumulative distribution function of peak ground acceleration and peak ground velocity, the fault normal component, in blue BB-SPEEDset, in red NES. And on the right, you see the distribution of the pulse period as a function of magnitude. And the idea of these checks that were more extended than the ones reported here was to check that there are no systematic bias in such a distribution of ground motion in BB-SPEEDset as compared with the NES dataset in the same magnitude and distance range. Another check that was done was also on the distribution of the between and within event residuals and the corresponding variability, again of BB-SPEEDset in comparison with NES. Here the residuals are computed with respect to a reference ground motion model, that is the Lanzano model. And in this plot you see on the left the between event residual and on the right the within event residual. I recall that the between event residual allows to understand if a particular event is more or less energetic than average, as predicted by an empirical ground motion model, while the within event residual indicates if a ground motion at a particular site is more or less intense than expected from empirical models. And here, these residuals are for PGA, peak ground velocity. A positive residual indicates that the motion is larger than the median prediction. And what we can see from these plots is that the residuals are around 0, so this is good. But the point that I wanted here to check also is on the variability. So the between event variability and the within event variability, so the event to event and the record to record variability, so the dispersion of these as obtained from BB-SPEEDset is comparable, consistent with the one from the NEST dataset. Finally, I would like to show some example on the level 3 validation that is more related to code-based engineering application. So the engineering validation of BB-SPEEDset was done following the workflow that is shown in this slide. The idea was to select two sets of real and simulated motion according to the same criteria based typically on spectral compatibility with a common target spectrum, and then these sets are used as input for the nonlinear structural dynamic analysis, and the outputs in terms of different engineering demand parameters are checked and compared to validate from an engineering perspective. To select the motion, we use the select and match. The software is a software, an in-house software that was developed at Politecnico di Milano. The interesting feature, the key feature of select and match is that it integrates both real and simulated data set. So is it possible to make queries on integrated data set and to extract ground motion that are according to defined, prescribed selection and compatibility criteria. So the motion, the two sets, real and simulated motion input signals were selected with select and match. The signals so we used for the recorded data set NGA and for the simulated data set BB-SPEEDset. Note that the signals were unscaled, and so the idea was to select them according to the same criteria to make them consistent to each other. And these were used as input for the nonlinear analysis of structure. The structure was simplified in this case, was an elastoplastic single degree of freedom structure. A single degree of freedom system, but with a nonlinear constitutive law, with different vibration period and different strength reduction factor. The engineering demand parameters were defined to capture both the peak response, so the inelastic to elastic displacement ratio, and the cyclic response. And the results are shown on the right-hand side, and you see these two engineering demand parameters as a function of period from BB-SPEEDset and from the NGA records. And again, the median are in line, apart from some deviation that you observed mainly in the low period range, and also the variability, the dispersion of the two sets of analysis are comparable. These kind of analyses were extended also to the case of more complex structures. I show just some sample results here, like in the case here for a 4-story reinforced concrete building that was representative of the pre-seismic buildings in Italy, of the Italian building stock. Also in this case, the signals, a wide set of signals were selected according to common criteria from real and simulated data set from BB-SPEEDset, and were used as input for nonlinear dynamic analysis for the structure. The idea here was to end up with seismic fragility curves for different limit states for this particular structural typology. And some results are shown on the bottom part of this slide, and you see in particular here the engineering demand parameter was the maximum interstory drift ratio, and you see the correlation, the relationship of the interstory drift ratio with different ground motion intensity measure, peak ground acceleration, peak ground velocity, and spectral average spectral acceleration. Here, this allows to make also some consideration about the efficiency of the different ground motion intensity measure when correlating with the damage of structure. And you see the peak ground acceleration is not well correlated, so you get, is not an efficient measure, sorry. You get a high dispersion in this relationship. While peak ground velocity and average spectral acceleration are efficient measures. And for the efficient measures, the behavior of BB-SPEEDset is absolutely comparable to that of real signals. I'm running out of time, so I just want to make some concluding remarks. As we have highlighted also in the discussion before, as one of the priority of the last workshop of the PAC-RIM workshop, the peer workshop, a key step to strengthen the engineering utilization of physics-based ground motion is the availability and dissemination of simulated ground motion. I think that there are different examples of international efforts to produce such ground motion. BB-SPEEDset from our side, the peer dataset, the CyberShake set of simulated motion. Also, there is also a recent experience in Turkey about the sigmoid dataset. Although this is related more on the stochastic simulation, so not on physics-based simulation. The main, I think, the main critical point is that validation is the key to make this simulated data set usable by the engineering community, but still there is no consensus on the validation procedures and acceptance criteria. And so probably also a more efforts in international collaboration to make, to define, to set up validation approaches, validation criteria, and acceptance criteria to validate such data set. BB-SPEEDset is an example of a validated data set of broadband near source ground motion. Of course, we are mainly focused on the near source ground motion, and it was created with the idea of sampling a rather wide magnitude range, different faulting styles and contexts, but of course, like a ground motion data set, it is under continuous development and validation. So acknowledgements, of course, this work is a this presentation reflects a collaborative work, and thank you.